Okay, I'm going to try to give you a visual idea of what a limit is because it can be pretty confusing for some reason. So, one way to think about it is the height of a function, the height a function is approaching, right? So, how tall, what is the height getting really, really close to when we are getting infinitely close to a given x value? So, this is what I mean. As we get really, really close, not when we're touching C, because then that's just algebra 1, right? Finding the height at a given value. This is when we're getting infinitely close. When I say infinitely close, let's say that's 5. When we're at 4.9999999, or maybe 5 point, and that goes on for a while. When we are here and here, what is the height approaching? So as we're really close, we get really, really close to the height. In fact, so close it's closer than that. And on the other side right here, as we get infinitely close, so it's the height a function is approaching when getting infinitely close to a given. That's very important. So if you have a test question that's talking about a limit, getting infinitely close to a given x value is a pretty important part of the definition, at least in my class. Okay, so the notation that I'll have you write. So the limit as x approaches, and maybe you're getting really close to 5, or maybe you're getting close to -8. C represents the x value that you're getting really close to. You go ahead and write the function, and then whatever that height is getting close to, you're going to put the height right there. All right, so for this function, it's just a quadratic. So the limit as x approaches 2, so you can see we're getting really, really close to 2. We're not touching 2, we're just getting really, really close to 2. What would the height be? So if I zoom in on that, and then I don't know if it'll let me scroll over. There we go. What height? That height is really, really close to 4. Well, that makes sense, doesn't it? When you substitute 2 into x squared, if we were at 2, we would be up there at 4. But as we get infinitely close to 2, notice we're getting infinitely close to 4. In fact, closer than that. It's more like, well, I can't. I think I froze that. All right, so let's look at another graph. So we have the square root function. So the limit as x approaches the square root of x, the limit as x approaches 1, the square root of x, well, we substitute 1 in the square root of x, and we get the height of 1. So as we get infinitely close to 1, we're going to be getting infinitely close to the height of 1. But here's kind of a twist. What happens when the function is not continuous? So we have this inverse function, but we're getting infinitely close to 0. Well, there's a vertical asymptote at 0. So on the right side over here, we're getting really, 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 really close to 0. I wish the reason I wrote it closer is because I couldn't zoom out far enough. We're going to get really, really close to 0. I mean, really, really, yeah, really, really close to the, I'm sorry, the vertical asymptote. But notice when we do get infinitely close to 0, what's the height? Well, here's the problem. There's this height and there's this height. Those two things don't agree. So when you have a function that is not continuous, and when you're approaching an asymptote, so the value, the x value, where there's an asymptote, And so each side does not agree. Or even if both sides did agree, but you're not approaching an actual value, you're headed towards infinity, the answer that you give is does not exist, and you can put capital D in E. So as x approaches 0, when either opposite sides of the 0 of the x values do not agree, or if on both sides they both were approaching infinity, you would still write does not exist for your answer. For a limit to exist, it has to be approaching a real number. Okay, however, what if I said the only part of the graph I want you to look at, the only part of the graph that I want you to look at is the left side. That raised negative sign means from the left. Well, now what is this height doing? Well, that's only one height, and it's headed towards negative infinity. So on one-sided limits, you actually can put where the graph is intending to be. Well, the intended height is it's going off towards negative infinity. And if we did the same thing, but with the right side, what is this behavior doing right here? Well, it's headed towards positive infinity. So the big idea is when you have continuous graphs, continuous functions, so continuous graphs, you will be approaching a height, right? Parabola, cubic, cube root, square root, square root, I kind of combined the notation in the graph, square root. All of these are continuous. As you're approaching an x value, you're going to get a height. But when the graph is discontinuous, meaning there's asymptotes involved, that is when there's three possibilities. Either does not exist, and that's when you're looking at both the left and the right side, and the heights are different. So that's when the limit as x approaches a c value. Then the limit as x approaches c from the left side, and from the right side. Two separate things. That is when the answer is probably, not always, but most of the time going to be positive or negative infinity. There are some situations where that's not the case, but if this right here is does not exist, then this will be maybe a negative number, and then this would be a positive number. But these two things would not agree. All right, that is it for kind of an introduction to what visually and just understanding what that definition would mean. What is a limit? It's the height a function is approaching as you are getting really, really infinitely close to an x value, but not touching the given x value. Given x value, very important.